Well, to continue our discussions regarding the isobaric data. Now, in this case, what do we have? We have P, we know P, and possibly we know x1. We will be in a position, we would be required to find out T and y1 say, right. So, therefore, in this particular case, there is a small amount of trial and error which is involved. Now, for most of the cases what we do, we assume some particular T. For that T you find out Pi saturated and your Pi saturated for the different components. Once you know Pi saturated, you know P. So, therefore, you will be in a position to find out the constants of the particular excess Gibbs free energy model that you are going to assume. So, from there you find out either A12 or B12, B21. Again, once you have found them out, you are now in a position to find out gamma i's for the other conditions, right. And so, therefore, from that particular gamma I, if you know xi and you know yi, then you are in a position to find out the P and the mole fractions in the vapor phase. If you know the mole fractions in the liquid phase, you are going to calculate it and going to see whether the constraint that I had mentioned, sigma xi or sigma yi equals to 1. It depends on what you are finding out. Are you finding out the liquid phase composition or the vapor phase composition? Find out the compositions for each of the components and see if the composition adds up to 1. If it adds up to 1, your temperature assumption was correct. If it does not, go for a different temperature assumption. The direction in which your assumption should proceed will be obvious once you find out whether your sigma xi is greater than 1 or less than 1. The methodology for finding it out is mentioned in this particular slide, but unless we take up a specific problem, this is not going to be clear to you. So, therefore, we go for a second problem here. This is an acetone carbon tetrachloride mixture. It is almost the same as the previous one, just the previous one was an isothermal data, this was an isobaric data. You are supposed to use both Van Laar as well as the 3 suffix Modulus equation, and you are supposed to find out T and y1. Your P is given here, it is 450 torr, and the x1s for 3 different x1s you are supposed to find it out. In this way also, the way we proceed, this is very it is all right. The small amount, some fragmentary data is given. So, based on this fragmentary data, you can take up this 55.29. Once you know T degree centigrade, you know the Antoine constants for acetone, for carbon tetrachloride. So, from here you are in a position to find out Pi saturated. You find that for acetone it is 739.18 torr, and for CCl4 it is 372.36 torr, right. So, therefore, these two you have found out, and obviously here in this case also you find that acetone has a higher saturated vapor pressure, and we designate this as component 1 and we designate this as component 2. So, now once we have found out these, now we are in a position to find out gamma 1. For the first condition, let us say x1 equals to 0.049, y1 equals to 0.189. So, therefore, for this particular condition we can find out gamma 1, it is 0.189 into 450 torr divided by 0.049 into 739.18, the P saturated. Gamma 1 it is 2.3482. Same way you can find out gamma 2, 0.811 into 450 by 0.951 into 372.36. This becomes 1.0306. Same approach as we have done the previous problems. This is x1 ln gamma 1 plus x2 ln gamma 2. This particular case, this is 0.0705. Now, suppose we start dealing with the Van Laar equation of state, or else initially the Van Laar equation of state. For the Van Laar equation of state, what do we get? We need to plot your x1 x2 by GE by RT. It is not a big deal, you can calculate it, it is going to be 0.6610. Now, once this is calculated, then you can repeat this particular calculation for other conditions as well, right. So, in this particular table, I have written down all the calculations which have been made. These I have demonstrated the calculations for one particular data. For this particular data, I have demonstrated the calculations. For other data, the calculations are going to be the same. So, this is the total table for the entire calculations that I have performed. Once this has been done, then from here you can find out you are required to find out x1 as 0.447. So, for this case y1 P1 saturated, everything can be obtained experimentally. Now, we have to find out theoretically. How to do it? Once you know this x1 x2 by this particular value. So, therefore, initially let us assume some t. Let us assume the t which is already provided here, which is 44.06. So, we can assume t equals to 44.06. x1 is 0.447, gamma 1 we have already found out, it is 1.24, and gamma 2 equals to 1.28. These things we have already found out from here, the gamma 1 and gamma 2 values. So, therefore, from here we are in a position to find out that for this particular case, gamma 1 is equal to, it is equal to 1.2555, gamma 2 equals to 1.2804, right. So, if you assume t equals to 44.06, you are in a position to find out P1 saturated, which is nothing but equal to 494.83 torr. P2 saturated you can find out 245.34 torr, from which you can find out Y1, it is just gamma 1 x1 P1 saturated by P. So, it is 1.2555, 0.447 into 494.83 divided by 450, 6171. Accordingly, y2 it is equals to 0.386. Add up y1 and y2, it is 1.0031. You can take this as more or less close to 1. If you want to go for slightly better values, then in that case you have to again change t. Now, you know that since sigma yi is greater than 1, you should reduce the t in this particular case. So, let us go for a second assumed t. Let us take this second assumed t, say as t equals to 42.48 degrees centigrade. Find out P1 saturated 466.42 torr, P2 saturated 230.70 torr, Y1 you can find it out, again Y2 find it out, add the two, you get more or less sigma yi equals to 1. So, therefore, this is your assumed thing is correct. So, therefore, from here we can find out, we can repeat this for different values of for the different x1 values which are given, and after repeating we find that the calculated T degree centigrade are this and the corresponding yi values are this. And you can compare them and you find that there is, although small, there is a mismatch between the calculated and the experimental values. Now, this was when we were using the Van Laar equation. Suppose we would like to do it for the 3 suffix Modulus equation. The situation is going to be the same. We are going to, in this particular case, instead of finding out GE by RT, this we will be finding out GE by RT x1 x2, and we will be plotting that, right. So, therefore, we can find this out, and we can plot it out. If we plot out GE by RT x1 x2 as a function of x1, again from the intercepts we know that at x1 equals to 0 we will get A12, here we are going to get A21, right. So, therefore, we can proceed in the similar fashion, and we can find out A12 and A21. In this particular case also, we find that A12 in this particular case is going to be 1.165, A21 is going to be 0.735, and then once we know this, we can find out x1 GE by RT as I have mentioned, and GE by RT x1 x2, and you can prepare this table. Once you have prepared this table, then you can find out ln gamma 1, ln gamma 2 for different x1 x2 values, and you can take up or you can assume a value of t. Naturally, the assumed value will be close to the experimental value, and for each particular assumed value you can find out y1 y2, and you can find out the summation, see if the summation is close to 1 or not, or else we go for a different sort of an assumption. Say for example, in this particular case, let us take up x1 equals to 0.447. I think I have already mentioned gamma 1 is 1.2696, gamma 2 is equal to 1.2736, t equals to, say at the first assumption is the experimental value. Naturally, as I have told you, for this case we have to start from the very beginning, from P1 saturated and P2 saturated. These are the values that we get. From here we get y1 equals to 0.6203, we get y2 equals to 0.3816, more or less we find that sigma yi equals to 1.0. So, accordingly we can calculate for the different cases also, and we get the yi calculated. Now, when we compare the experimental versus the calculated values for both the Van Laar and the Modulus equation in both the problems that we have dealt with, we find that the Van Laar equation appears to be much more accurate in this particular cases. Well, so what we do? We have been discussing the reduction of isothermal and isobaric data from some fragmentary experimental data if we have that. Now, we know that the calculations of gammas and the calculation of the corresponding constants for the excess Gibbs free energy model, it becomes much simpler if we know that there is an azeotrope formation at any particular composition, right. Why does it happen? We have already discussed. At the azeotropic point, what happens? x1 becomes equals to y1, and naturally under this condition y1 becomes equals to p by p1 saturated, isn't it? So, therefore, we get y1 equals to p by p1 saturated, gamma 2 becomes p by p2 saturated. So, therefore, the finding out of gamma 1, gamma 2 becomes very easy at the azeotropic point. Once we have found these out, we can find out ln gamma 1, ln gamma 2, and then we can select any of the excess Gibbs free energy model. It can be Van Laar or the Modulus. So, from here we find out the constants. From both these we can find out the constants A12, A21 or B12, B21 as the case may be. Once we know this, we can find out gamma 1, gamma 2 for other compositions, and once we know that, we are in a position to find out P, and we are in a position to find out y1. Let us take up a specific problem in order to discuss this. Methanol acetone. We know that it forms an azeotrope at 760 torr with x1 equals to 0.2 and T equals to 55.7 degrees centigrade. It is given here. We are required to predict the PXY data under this condition. finding out gamma 1. So, therefore, what are we supposed to do under this particular condition? We can find out the P1 saturated and the P2 saturated, and we can find out the gamma 1 and gamma 2 for this particular case, is not it? So, therefore, at T it is given T equals to 55.7 degree centigrade, right. For this particular case, what is P saturated for methanol? This is equal to 530.97 torr. P saturated for acetone 749.65 torr. Agreed. What is gamma methanol say? Under this particular condition, this becomes 730 by 530.97, 1.4313, which gives ln gamma methanol as 0.3607. Similarly, for the acetone case, we get this is as 760 by 749.65, which gives us 1.0138, which gives us ln gamma acetone as 0.0137. Now, we can either take up the Van Laar equation or the Modulus equation, no matter whatever we take up. If we take a Van Laar equation, we can find out B12 and B21. We know gamma 1, we know x2, x1 at the azeotropic point. So, for the azeotropic point, we will in a position to find out B12 and B21. Once we can find out B12 and B21 at the azeotropic point, we know that it does not vary with composition. So, therefore, we can find out ln gamma 1 and ln gamma 2 for other x1, x2 values as well, and then from there we can generate it, right. So, in this particular case, we find our B12 is 0.4786, B21 was 0.7878, and for this particular case, say at x1 equals to 0.1. So, therefore, we have found out everything for the azeotropic point. Now, let us go to some other composition. Say at x1 equals to 0.1. For this, we can find out gamma 1. I have already shown you the equations from where you are supposed to find out gamma 1 and gamma 2. So, therefore, in this case we find gamma 1 equals to 1.5219, gamma 2 is 1.0032. So, P in this case 757.62 torr, Y1 comes to as 0.1067, right. Now, in a similar way we can find out the gamma 1, gamma 2, P and Y1 for other compositions in the liquid phase, and in this way we can generate the Pxy data for using the Van Laar equation in a much more simpler fashion, provided we know that there was an azeotrope at a specific condition of x1 equals to 0.2. Same thing can be repeated for the Modulus equation as well. For the Modulus equation also, we can find out A12 and A21. How to do it? What is A12? 2 ln, if you reduce the equation, you find that this is going to be 2 ln gamma 2 plus x2 minus x1 ln gamma 1 by x2 square. This becomes 0.4752. Similar way we can find out A21, just in a similar way 2 ln gamma 1 by x2 minus x1 minus x2 ln gamma 2 by x1 square. This becomes 0.69. Once we know these two, then naturally we know A12, we know A21. We are in a position now to find out ln gamma 1, ln gamma 2 for different values of x2 and x1. This has been done here, right. So, here we have repeated the same thing. For example, suppose we want to find out ln gamma 1, it is x2 square, you can just compare it, since it is A12 plus 2 into A21 minus A12 into x1, this reduces to x2 square 0.4752 plus 0.442224, right. Same way you can find out ln gamma 2, it will be x1 square into 0.6963 minus 0.4422 sorry, very sorry, x1, this is x2, right. So, we can find this out. Once we know this, then at say x1 equals to 0.1, gamma 1 this becomes 1.5231, gamma 2 becomes 1.0030, p you can calculate 757.58 torr, y1 it becomes 0.1068, right. In the similar way you can calculate it for other values as well, for 0.3, 0.5, 0.7, 0.9, and in this way you can generate the entire set of data using 3 suffix Modulus equation. Well, we can take up one more problem as well concerning the azeotrope. Say for instance this particular problem. Here it is given that for a binary mixture, both the components they obey the 2 suffix Modulus equation, right. When they obey the 2 suffix Modulus equation, we know ln gamma 1 equals to ax2 square, ln gamma 2 equals to ax1 square. And you are required to predict the condition of azeotrope and the corresponding azeotropic, the condition and the corresponding azeotropic composition. How to proceed? What are the things that you know? You know at the azeotropic point y1 equals to x1, at azeotropic point, you know it already, right. Accordingly, what is gamma 1 you know, we just now did p by p1 saturated, you know gamma 2 p by p2 saturated, you know what is ln gamma 1 is ln of this, ln gamma 2 is ln of this. Now, suppose you subtract one from the other, what will you get? You will get ln p2 saturated by p1 saturated is nothing but a into x2 square minus x1 square, isn't it? And this is nothing but equals to a into 1 minus 2x1. Agreed? So, therefore, what is x? So, therefore, we find that the condition of the azeotrope should be related to this particular condition. And where does the and for this particular condition, you know that a into 1 minus 2x1 equals to this. So, from there you can find out x1, this is nothing but half into 1 minus 1 by a ln p2 saturated by p1 saturated. So, this is the corresponding the composition where the azeotrope forms. This is the liquid phase composition of component where 1 where azeotrope forms. Now, under what condition does it form? We know that the azeotrope has to form between 0 and between the composition of x1 lying between 0 and 1. So, therefore, azeotrope forms for 0 less than x1 less than 1, right. So, for x1 equals to 0, what do you get? You get x1 equals to 0, this part has to be equal to 0. For x1 equals to 1, you know 2 has to be equal to this particular part. So, therefore, once you have obtained them, you find that for x1 equals to 0, a should be ln p2 saturated by p1 saturated, and for x1 equals to 1, a should be minus ln p2 saturated by p1 saturated. So, therefore, when does this system form an azeotrope? Can you tell me? System forms an azeotrope between x equals to 0 to 1. So, it has to form an azeotrope when a has to be greater than ln p2 saturated by p1 saturated. Now, we have a minus value, we have a plus value. So, it is safest if we can denote it as a has to be greater than the absolute value of ln p2 by p1 saturated for an azeotrope to be formed. Well, so there is one other case also where the calculation of gammas, or in other words the VLE calculation, becomes much more simpler. This is usually it is quite well practiced for hydrocarbons, and this is known as the K factor. We can use the K factor and find out the VLE data for hydrocarbons in quite a simple fashion. Now, what is this K factor? Let us see. we find that for a mixture of hydrocarbons, usually the intermolecular forces are quite weak. Now, since the intermolecular forces are quite weak, so therefore, under this particular condition, we find that this was the original equation that we had taken. Now, when the intermolecular forces are weak, again we can assume the vapor phase to behave as an ideal gas or ideal mixture, although it is important to remember that the individual gases, they do not behave as ideal gases. So, actually for that case, what happens? For that particular situation, we find that phi I v becomes equals to this particular term, this phi I v, it is equal to the pure component phi I, right. And therefore, and usually we find that the liquid phase, it behaves ideally. So, therefore, usually for hydrocarbons we find that this term becomes equal to 1, this term becomes equal to 1, this more or less this becomes equal to the pure component vapor phase, and this term also it disappears off. So, therefore, very frequently what is done is Ki for each particular component, the K factor is defined, which is nothing but the ratio of the mole fractions in the vapor and the liquid phase. Now, from this equation we find what should be the K factors. It is gamma I, which is usually not there, Pi saturated, phi I saturated by phi I v into P. Exponential term definitely remains, because the liquid behaves as an ideal mixture, but if you are dealing with high pressures, then the Poynting correction factor can be found out. So, therefore, what did we find? By assuming that phi I v equals to phi I v, or in other words, the gas mixture behaves as an ideal solution, we found out that we are in a position to find out Ki from all the properties of the pure components of, or rather we can find out the Ki from the pure component properties of component I in the vapor phase and in the liquid phase. And therefore, very frequently what we find that Ki's have been calculated for a large number of hydrocarbon gases, and then they are tabulated as functions of T and P. We find naturally, since they are properties of the pure components, so they are functions of the pure component properties. So, therefore, they are functions of T and P, and lot of effort has been put to plot the K values of individual hydrocarbons as functions of T and P, either in the tabular form or as monograms. Now, the monogram which has been proposed by D. Priester and then it has been modified later is as shown in this particular here. Here we find that the monograms are presented for the low temperature range and high temperature range, and these, with the help of these monograms, where we find that for each and every hydrocarbon gases, if we know the temperature, we know the pressure, we are in a position to find out the K values, the calculation becomes pretty simple. We will just be doing two problems and finish off this part. First problem is a vapor mixture. Now, here it is written that this particular vapor mixture, it has Y methane, it is 0.2, it is written there Y methane is 0.2, Y ethane, this is 0.3, Y propane, it is 0.5, T is given as 30 degrees centigrade. What are you supposed to find? You are supposed to determine the pressure at which condensation begins. How to proceed with this particular case? Since P is not given, you are not in a position to use this particular K factor chart. You have to guess some particular P. So, let us see, for the time being, let me take the first guess as 2.15 MPa. Once I have guessed this, T equals to 30 degrees centigrade, we can draw a straight line from 2.15 megapascal, it is roughly here, and it is at about the temperature is 30 degrees centigrade. So, if we draw a line, we are in a position to find out the Y factors for methane, for ethane and for propane. Let us see what are the Y factors. We find that for methane the K factor it is 8.1. For ethane it is 1.82. If you draw this straight line, you will be able to locate it, and for propane it is 0.62. So, once you know this, once you know the Y values, it is very easy to find out the corresponding mole fractions in the liquid phase, isn't it? This comes to a 0.0247, this comes to about 0.1648, and for the propane case it reduces to 0.8065. If you take the sigma xi in this case, it is almost equal to 0.996. So, therefore, we can say that my assumption of pressure was more or less correct. For greater accuracy, you need to alter this slightly, and then if you get sigma xi greater than 1, then by linear interpolation you can take the intermediate pressure. Okay. Accordingly, you can find out the due pressure. Once you know the due pressure, then with the due pressure and with the temperature you can find out the K values once more, and using the K values you can find out the composition of the first liquid which appears. This we had done by when the vapor phase composition was given. We can also proceed similarly if the liquid phase composition is given as well. There is one more problem which we can do. In this particular case, we find that we find that in this particular case X ethylene is provided and X propylene it is there. This is C2H4 and C3H6. This is 0.25 we know, this is 0.75 we know. It was initial temperature was minus 40 degree, the pressure is given, it is 1 MPa. Now, it is required to find out the temperature at which the first vapor is going to appear. Again the same thing, there we had assumed the pressure, here we are going to assume the temperature. Say for the time being we assume some particular temperature, say close to minus 10 degrees centigrade or something, maybe minus 8.5 or something. Actually minus 8.5 is the correct answer, I know. So, we can start with minus 10 degrees centigrade, then you can assume minus 6 or 5, and then by linear interpolation you can find out the actual temperature. Once you know this temperature, you know the pressure. Again you are supposed to draw, it is not a straight line, that you are supposed to draw a straight line, and then you are supposed to find where it cuts the ethylene, where it cuts the propylene. So, in this particular case we find that your K ethylene, if you observe, your K ethylene is going to be 2.55, provided I have assumed it as minus 8.5 degrees centigrade, P equals to 1 MPa, and we find that your K propylene is going to be 0.49 I guess, yeah, it is going to be 0.49, right. So, from there you can find out your Y ethylene, this is going to be 0.6375, and your Y propylene it is going to be about 0.3675. So, the sigma yi that you are going to get is 1.0050. So, therefore, you can say that the bubble temperature was nothing but equal to minus 8.5 degrees centigrade, and the corresponding vapor composition can be given by the compositions that we have found out. The only thing which we need to do is that we have to start with a guess value, it is not very difficult to guess it properly, because it has to lie between the boiling points of the two liquids. So, we can start with, and more or less we know the compositions. So, we can start with a weighted mean boiling point, and we can go and we can proceed. So, in this particular way, what I did was, we discussed different non-ideal solutions, the methods of generating the complete PXY or the TXY data from fragmentary data, and how the situation gets simplified when we are dealing with azeotropic data, when there is an azeotrope formation, and with the use of K factors, how the situation gets simplified when we are dealing with hydrocarbon mixtures. Now, we have been dealing with a large amount of rather we have been discussing for quite some time regarding the VLE data of different non-ideal solutions. It is important for us to know that since we are dealing with so much of experimental data, whether the data that we have collected or generated is thermodynamically consistent or not, whether the data is reliable, whether we can proceed with the data. So, in the next class we deal with thermodynamic consistency of VLE data before we proceed with any other topic. Thank you very much.